Thank you very much. So, this is a talk about applying cloud-native principles to data science. In 2016, Microsoft made a very gutsy move, and they released a new breed of chatbot into the public domain. The company's website claimed that it had been built using relevant public data, that it had been modeled, cleaned, and filtered. You may have heard of it. It was called Tay.ai. The purpose of the bot was to respond to tweets in a humanistic manner. You could send it questions on Twitter using its handle, and it did a really good job of answering like a youth, actually. I say a youth because I didn't understand a lot of the acronyms it used. But when it was released, everything was actually going swimmingly, and it worked remarkably well. It really did sound like a human was on the other end. But when a big tech company like this releases a product like this, usually the first users of this service are engineers. And given that you're all engineers in the room, would you, A, test out this service, appreciate it for what it is, and ask it sensible questions? Or B, would you try and break it? Would you send it the most horrific things that you could think of in order to try and force it to give a silly answer? Well, engineers are a sadistic bunch, and you can guess which option they chose. The bot went from a mild-mannered, well-answering chatbot to a sexist, racist, genocidal Nazi in about 24 hours. You've got a collection of tweets you can see there where it started off, looking quite good, and we ended up with Hitler. If you end up with Hitler, you know it's gone wrong. One of my favorite tweets, actually, was about a British comedian called Ricky Gervais, and it had a very, decent enough question: is Ricky Gervais an atheist? The response: Ricky Gervais learned totalitarianism from Adolf Hitler, the inventor of atheism. Now, for all I know about Hitler, I don't think that's his most famous trait. But I'll give it 10 out of 10 for imagination for that one. And ultimately, the result of this wonderful experiment, 24 hours later, it was dead, gone. And although that's quite a hilarious story, I'm actually quite impressed with Microsoft. It was a very gutsy move to allow this to happen. They managed to deliver something that was really quite impressive. But I think, and this is just speculation, that I think that some of Microsoft's traditional organizational stuff got in the way. I think that if people were able to spot these problems, and they were in a position to be able to spot these problems, then they could have stopped it before something like this happened. And that's really about what this talk is about today. So, in normal life, tradition is a fantastic and important part of culture, it's a cultural meme. But in engineering, it's actually the harbor of bad habits. If we stick to traditions, then we tend to repeat the same mistakes. I used to work as more in the data science field than in software engineering. And what we used to do was I would go away, and I would write my models and do my research. And then the only thing that everybody else would see was just this mass of code, which I would throw to software engineers. And I would say, there you go, software engineers, I've finished my job. Now it's your turn. You implement it. And obviously, most of the time, that just didn't work. Some of the time, it partially worked, but it never worked as well as it should have done. I actually spoke to a client the other day, and he was worried that he had paid for a project for his company he sent some data off to a research arm, and he was worried that the work that these researchers were doing were kind of not really applicable in real life. The words he used, he thought it was a bit too academic with the words he used. And what he meant was the types of things that they were coming up with were not really realistic and relevant to modern-day industrial software. So yeah, tradition is a bit of a problem. But traditionally, data scientists have worked towards a certain type of model. This is a model called the Cross-Industry Standard Practice for Data Mining, and this is the nearest thing we've got to a process in data science. You'll see that there's lots of loops in this process, and that's just indicative of the fact that most of data science is kind of open-ended and continuous. It never really stops. The problem with this is that pretty much all of these steps are, they're very individual, and they don't scale very well. So the first problem is the deployment phase. As I just said, when I was a data scientist, I would throw my models over to the software engineers, and then I would never see it ever again. I kind of think this is probably something that happened at Microsoft. We get the software engineers that have not been trained in data science. I give them, poorly documented, uninterpretable code, and expect them to understand it and implement it efficiently. It's never going to happen. And then we start going through the other parts of the model. The first is data understanding. This is a major issue in data science because the data is the most important part of the problem. And the data understanding part, we rely on domain experts in order to interpret the data. So we had a great talk earlier on from Feynman about how he was working on the music domain. He was working with, if you weren't there, he was working with classical music. And to a normal data scientist, you would know nothing about the terminology used in music. But throughout his years of doing this research, he finally became a domain expert. But it took years and years of work and years of time. So that's a good example of that. Data preparation is another problem area because it's often done by one person and it's only done once. So what happens is you get one guy that really delves into the data and they're the ones that really understand it, but it's kind of it's hard to reproduce because only one person understands it and the output is again just this amorphous blob of software which takes messy data and spits out good data. And then finally, modeling. This is a little bit easier to reason about if you have more and more people understanding the types of models used and how to do modeling. But the issue with modeling is that, again, this is a very one-person-only process because the process usually involves trying lots of different things and basically picking the best one. But that process, that trial and error, is never recorded anywhere. The only output is the model, That is the answer. So if we want to scale this past one person, then we need to, usually what happens is the second person repeats all the same mistakes and that actually ends up at a different result because, his biases and his preferences towards algorithms usually ends up in a different model. So, the whole part of that side of the model is kind of like a murky canal, It's like a mucky Amsterdam canal. The ships can go up and down, but you wouldn't want to jump in and follow it. And then if at the end of all that, we've got the operation side, the deployment side, we've got the vast majority of the data science research phase that's not going well, actually the vast majority of projects fail because there's a lack of business understanding. And that's either because the business doesn't understand the technical implications that they're proposing, or the tech guys don't understand the business problem enough. So a whole host of problems. So I think what I'm going to do now is I'm going to ignore the business side a little bit, because that is actually a separate problem in itself, and you're all tech guys and gals. So I'm just going to stick to these three distinct phases. We've got the research phase, which was the bit that talks about understanding the data, massaging the data, and producing the data in the model. We've got the build phase, trying to prove we're doing what we're doing is correct, and then the actual deployment phase, the bit that we want to rush into production. So yeah, the research phase consists of the initial data science. That can be anything from performing experiments, gathering more data, preparation, data cleaning, modeling, all that good stuff. This is called the research phase because it is a very scientific process, and the biggest problem with that is that it's inherently open-ended, and therefore it's very high risk. So there is a high probability of failure at this point because you might find that either you don't have the data to do the job properly, or you just can't do the job because it's intractable for some reason. So stepping back a bit, believe it or not, Britain actually had a very rich motoring heritage. You might not think it these days. You might think of Germany or something like that. But there's a manufacturing plant near Oxford, which started in 1913. So this is a picture from that same manufacturing plant in 1943. And from about then till the 1970s, it was owned by a company called British Leyland. This is a picture of their manufacturing line building Cromwell tanks for World War II. By the time it got to the 70s, it was building this little car, which you probably all recognize. But at the start and during the 70s, things started going wrong. And the ultimate reason why they went wrong was because there were better, cheaper alternatives available. Other companies were investing in the automation of these lines in order to produce better quality and cheaper products. And, you know, when we talk about software engineering really is, it's just converting a process into code so that we can automate it. That's all it is. That's where I should have said that word. And today, I think that data science is actually the automation of the data. So we're starting to see like a three-tier hierarchy here between, you know, we've got data science at the bottom, which is taking all of the data and automating things based upon that data to feed into the process. So I think that data science and software engineering actually make a very good fit. They go together very well because the data and the science feeds into the software, which then feeds into the value that you're trying to provide. And this is a picture of the same manufacturing plant in 2013. So this is 100 years after the manufacturing plant opened. And you can now see that it's far more automated, and there's basically no humans there. And that allows this company to build better, more reliable cars. And as you probably know, this company is now owned by BMW. So, you know, the great golden English company was eaten up by German manufacturers. Damn it. So yeah, anyway, my point is that I think software engineers, us as software engineers, are actually in a really good position to actually push ourselves into data science, not the other way around, because we've come away with all of the things that we've learned during this, you know, more traditional automation phase, and we can start applying it to data science. Because the fact is, like, at the moment, none of this happens in data science at the moment. And this leads me to data science's dirty, dirty little secret. And the little secret is that the vast majority of your effort and time and engineering skill as a data scientist goes into the data, just messing around with the data incessantly. You know, we are fixing problems with the data, we are imputing missing values, we are removing invalid data, and so on and so on and so on. And the vast majority of the final performance of the model is based upon how much you can improve that data, not on the model. So, you know, we've had two great, fantastic talks this morning, you know, all about deep learning, all about very sexy technologies, but that's a very Silicon Valley problem. No offense to the Silicon Valley guys, but that's a very Silicon Valley problem. For everybody else outside of Silicon Valley, we're still living in a world where, you know, it is the simple techniques that really make a difference. And it doesn't have to be a complex model. Simple things can go a long way. And one of the biggest issues with this process is that this discovery, this fixing the data, this understanding the data, as I said, it's only done by one person. So I think actually this is just a problem of visibility. There is very little visibility within data science. There's only generally one person that's working on a problem at a time, and it's, you know, it's very difficult to scale, or at least it's very inefficient to scale. Over the years, software engineering has done a really great job in improving this, because we had exactly the same problems. You know, we could distribute binaries quite effectively, but when it came to source code, we've gone through, you know, decades of trying to improve the visibility and the resiliency of our source code. And thankfully, data science is finally starting to get there. And these two tools in particular have been very prolific. So you probably all know one of those. So I'm not going to talk about that. But the second is a notebook. Some of you have probably come across it, but you've maybe not. So I'll just introduce it. So this is Jupyter Notebooks. It's an evolution of IPython notebooks. The idea is that inside the notebook, there is a series of cells, and each cell can either be marked down or it can be code. What this has done is that it has single-handedly improved the visibility from pretty much 0 all the way to almost as good as it's get. I think this is actually probably better than software engineering in terms of visibility. What it means is when I first get some data and I'm doing my analysis, I can document everything I do, even the mistakes. I can write the code, I can write words if I need to, and whenever anybody else wants to repeat that process, they can just come along and read this like a document. If they want to, they can come in and they can actually start playing with the code. They can start doing tests. If you think, oh, I think your model's rubbish, I'm going to try another model, or I'm going to try some different parameters, it's very easy for someone to just come in, change something, and run it. So this is a very iterative, a very visual way of doing data science. And yeah, it's made a huge impact. And then when you team it up with Git, then I think we've got the holy grail of repeatability from Git and visibility from Jupyter Notebooks. And even like it's something we don't take for granted. I think it's something we take for granted. For example, like when we're looking at code, normal software code, we're using GitHub and GitLab and whatever, just the online viewers to view code far more often than we actually think that we are. And that alone is super helpful for the visibility there. And that is fine, very good, and a huge advancement for individual developers. But how do we scale it to multiple developers? We do that with another project from Jupyter called Jupyter Hub. And it's quite a simple architecture, as you can see. Main parts comprise of a HTTP proxy. We've got the individual notebook. So this notebook part is the bit I've just explained to you, the Jupyter Notebook. And then we've got a couple of user-based stuff on the left-hand side there to handle multi-tenant instances. But the most interesting thing is this thing, the spawner. Because what we could do is we can override that spawner and plug in a whole range of tools. We can plug in Docker, and we can start spinning up Docker containers. We can start spinning up, Mesos containers on an orchestrator. We could spin it up in some sort of cloud-based environment. It's incredibly useful. Possibly my favorite is we can start Kubernetes jobs, start pods with our own containers in. And, as software engineers, we know that this provides us with a huge amount of flexibility. We can simply scale out when we need to. If we've got more developers working on a different problem, just add more pods. If you need bigger machines, just scale out the number of machines. We can select our machines, whether we want GPUs or CPUs. It's all light years ahead of data science. So we've got the visibility. We've now started to containerize the process. So this is, two core tenets of cloud native: containers, visibility. Now let's build on. Now let's move on to the build phase, not build on to the move phase. So we touched on this at the start, but in the past and continuing today, it still happens today. Data scientists is a very general term. I don't necessarily mean people with PhDs that are working with high-level tools, deep learning, this, that, and the other. Just normal people just working with normal data. They come up with an idea, maybe a simple model, they throw it over to the software engineers. This is completely analogous to where software engineering was about 10 years ago. Software engineers would take their binaries, their software, throw it over to the ops guys. And we're combating that with the idea of DevOps. So I think that there's an equivalent shift that needs to happen with data scientists. The data scientists need to become more integrated with the software engineers and ultimately more integrated with the ops people as well. So, data ops, if you were. And at best, if we don't have that, at best we have inefficient models. But at worst, and what's more likely to happen is that things don't happen at all. And if you don't get that transition right, then you just end up with bad products. And talking of AI and robots, I love that video of the lipstick robot, Simone Gert there. Hilarious. Oh, you're all boring. I find that funny. I'm gonna laugh. And so how do we improve this? Well, like we saw from the DevOps transition from Dev and Ops, much of the problem is actually a people problem. It's about getting people to accept that their role is changing, and it's changing for the better, for the benefit of everyone. And that's okay, but it's a bit boring. What we can do, technically, is start to enforce quality. We can enforce quality with, surprise, surprise, continuous deployment, continuous integration. This is a classic continuous delivery pipeline. I'm sure you all know this. The engineer, would commit his code, it would go onto a build server, it would run through a pipeline, be deployed into production. Now, the pipeline is possibly the most important part of this entire process, and it needs to be customized to your domain and your problem. I always like talking about the testing triangle. This is quite common in the CI literature. If you haven't seen it before, it's an image where on the x-axis, we've got the number of tests, and on the y-axis, we've got like the scope or the depth of the test. So at the bottom, we've got unit tests we have very large numbers of unit tests that are testing very small bits of code, all the way up to the top, where we have very few tests, acceptance tests, but they're testing a huge amount of code. That testing process is possibly the most important part of the build phase. If you don't test your models, then you end up with something like this. This is my colleague. He was trying to book a flight from Amsterdam to Prague, I think, and Kayak kindly recommended the flight, meh. That was a direct output of one of their recommendations models. It was meh. So that was, for this guy, he obviously couldn't book a flight. They lost his revenue. They lost his money. I dread to imagine how many other people were using the site at the same time, and they all received big meh. And they must have lost a lot of money. I think if anything, is a clear indication that the data science people need to be more integrated into the operations of their actual software, because they're the only ones that know, how to implement monitoring the best way. They know how to fix it if it goes wrong. And then we get on to the deploy phase. And this is a bit more difficult to talk about because it's a bit more domain specific. It's very tech stack specific. So it depends what technology stack you're using. But I can generalize it a little bit by talking about containers. But I mean, ultimately, the goals are exactly the same. We want our software to be reactive, resilient, and reproducible. We want it to be reactive so that when we have changes to the outside world, we can scale up and scale down as accordingly. We want it to be resilient, so if it ever fails, it needs to automatically repair itself. And reproducible. If we can quickly reproduce our cluster in another location or for testing or something, that improves testability. And that kind of represents this tiny little arrow in the build pipeline. And even in continuous delivery, this is often overlooked. And it is always represented by a little arrow, as if it's like this simple thing where you just push to production. Flowers, smiley faces, done. And it's never like that. It's a bit more difficult and far more specific. And there's a lot of engineering effort that is spent, trying to push this out to production. For data science land, one of the easiest things we can do is bring in containers again. So how do you do that? Well, you have some sort of model. You can quite easily stuff that into a container. And if you've just got interfaces and routers, then they're all pretty standardized. Once you've got to that point, then it becomes much easier to not only make sure it runs on your machine and it works the same way in production, but also it's easier for other people to reason about as well, because you're reducing the domain that people have to understand in order to use your service. And that model can be anything. It could be just a simple Python model. It can be Theano, derivative, TensorFlow, whatever. And if you're into sort of more streaming technologies, and we can easily apply streaming technologies here as well. If we just package up the whatever it is in your particular streaming package that you're using, like some sort of Spark executor, it's still perfectly reasonable to do that. And that fits really nicely into the testing triangle, because we can build that container as part of our delivery pipeline and start testing that container as opposed to just testing the code itself. So, it's all fairly standard stuff that everybody aims for, but it's amazing at how much this doesn't happen in real life in data science. And then finally, we can simply stuff that container into production however you want, using some sort of orchestrator, or if you're using some sort of streaming-based system, selecting GPUs and CPUs. It's the ultimate in flexibility. If it works there, if it works on your laptop, it doesn't matter. And just to finally push home, one of this is a slightly different domain, and I know there's a few ThoughtWorks people here today, so I've got to be a little bit careful. They're a great company, an amazing company, but their marketing department, I think, also needs to be integrated into production as well, because they sent out this email last week, and I would be really interested in finding out what ThoughtWorks seismic shits are. I find that really fascinating. Actually, I think this is a genius move by the marketing department, because so many people were talking about this in the office, and I think that's done far more for ThoughtWorks than anything they could have sent out. So well done, that marketing person that made that. OK, so now I have a quick demo demonstrating all of these concepts together. I've tried to think up a simple example. My example is a whiskey shop. So my business requirement is I have a client, which is a whiskey shop, because I like whiskey, and they have come to me because they want to provide a USP in the fact that they can recommend better whiskies than anybody else. But the problem is they want this to be able to scale. They can't really afford to employ whiskey experts at every single one of their shops, so it's much more efficient to write an algorithm to do that for them. So the requirements are they want somebody to pass a favorite whiskey in, and they want recommendations out. They want to start off with a limited set of whiskies, but want to be able to update their data in the model in the future. This is all available on my Git repository. You can get that for it's all open source, and it's pretty simple. The algorithm I'm using for this is pretty noddy. It's the kind of famous standard whiskey data set. And just to cover that a little bit, it's a simple nearest neighbor algorithm. So if you have two whiskies, so all whiskies are characterized by a set of numbers where the numbers correspond to a particular feature of that whiskey. So the features might be smokiness or sweetness, toffee, things like that. So what would happen is that it would calculate the distance between someone's chosen whiskey and all other whiskies. And then we would pick the top 5 or 10 or whatever recommendations based upon that. So pretty simple, but works remarkably effectively. But the key thing here is got a full continuous delivery pipeline. So all of those stages have all been implemented with unit tests and mock data and real data and acceptance tests. And I've used Jupyter Notebook for the initial analysis. And we're able to insert new data simply by stuffing it into Git and then watching it flow through the pipeline. So hopefully this is going to play. It is, excellent. So I've made a video here because, as you probably know, a lot of this takes a lot of time. So now I'm just messing around with Terraform, creating my new infrastructure for this project. And we're going about 10 times speed at the moment, blah, 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 blah. Blah, 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 blah. You're probably all used to seeing this. And then the end result is a working server in the cloud with some initial software deployed. Oh, dearie me. Can you see the bottom of that screen? Oh, you can. It's just this monitor. It's OK. So what I've just done there is I'm just fixing bugs because it didn't work. And finally, we've got our algorithm actually working. So this is running out of a container. And when I curl a container, then I get my recommendations back. So simple REST API testing. I've passed in Macallan. That's my favorite whiskey. And so I'm going to get these recommendations here. Awesome. So first job, as a software engineer, I've figured out that there's maybe a little bug in my code. So I've got you see I've asked for Macallan there, and it's actually returned Macallan as one of the recommendations. So that's a bit pointless. So that's my first bug. I'm going to go and try and fix that. So now I'm just inside the code, and I'm just going to edit that code. I'm going to basically ignore that first value there when I output my recommendations, and we're going to write that back. Then we're going to push that to the repository. There we go. And then we're going to watch our pipeline. So this is quite cool. We've got a pipeline here where we've got all of the tests running in parallel. If those tests pass, then we go into a registry step, which pushes that file to a registry. And then we'll talk about the deploy in a little bit. But all of those stages are just implemented with a simple YAML script, you know. And but the beauty is that we're actually using realistic data to test this software, which kind of isn't something that happens in real life. I haven't noticed, you know. So what tends to happen is that you implement it manually, and then you test it manually, and then the software engineers have some sort of dummy data that they should use in their tests, and they have some expected output. But it's a very small, you know, it's usually mock data, it's usually not realistic, and it's certainly not real data. And then at the end of the process, the data scientist would come to the software engineer and manually test his software to see if it's okay. You know, it's a hugely manual and a very poorly managed process. If we can stuff all of that into a pipeline, like we've done just here, thumbs up. Okay, so all our tests have passed. It's now being pushed to the registry. And once it gets pushed to the registry, then it will be deployed to the server. For this, all I've done is just done a real hacky, let's SSH into the server and just do a Docker pull, Docker run, which isn't great. If I had more time, I'd probably deploy it to Kubernetes or something. But it works, and it demonstrates it quite well. So I'm just going to watch that container on the server now. And in a minute, we'll see that container. There you go. So now it's just been deleted, and it's going to be recreated there. So that's the deployment phase in action. So if we now go back and actually test this new service, then hopefully we should see a better output. There we go. Search for the same thing again, Macallan again. And you can see we've removed Macallan from the first entry there. Fantastic. And that's okay, and that's kind of a traditional software task, but it's something that a software engineer would normally do, not a data scientist. So again, the focus here is to try and get the data scientist involved in the software engineering, or vice versa. If now we have a second data scientist or another engineer that, you know what, I don't like some of your data, I'm going to change the model. So I'm going into the IPython notebook, and I'm looking at what the previous person has done. And now you're just going to see me hacking around trying to get something working. But the idea is here that this is the process that an engineer would normally go through when he's trying to implement a new model, or I think in this case I'm trying to insert some new data. Lots of errors. Finally figure out how to do it. Yep, still not right. Data's the wrong size. How do I do it? There we go. There was a few minutes there where I was on Stack Overflow. That's why the pause was there. There we go. It's worked. And so I've generated some new data. I've pushed that to the repository. And now we're going through the build pipeline again. So this is the same build pipeline, but with a change of data. So we haven't changed the model now. So it's important to have the data almost as part of the model, if you can. Maybe the data's too big, but if you can, it's really useful to be in there because you can catch bugs like this. So I think what we just saw there was some of the tests failed because the data had become in such a state that it wasn't giving out the output that it should have done. So now, this time, instead of adding data, I'm going to just remove some data. So I've removed the whiskey, and we've repushed it. I think what I find out now is that I've actually caused some of my unit tests to fail by removing one of the whiskeys that was in my unit test. So I'm just having to fix that. There you go. There was a commit there saying it's really working now, smiley face. And there we go. Our tests are finally passing. And once again, we're going through the registry. And we get to deploy it. There it is. Come on, do it. Do it. Do it. It'll get there eventually. You know, the result is the finally deployed model. There we go, finally, with the new data, all without touching the model, but still going through the pipeline to guarantee that not only our model is valid, but the data makes sense, and when we throw different data and new data at it, it still makes sense. So you can imagine trying to apply this to your own stuff, that if you have got requirements for like accuracy requirements, you could make that a hard and fast rule in your pipeline to fail when your model accuracy decreases to a certain point. And that's it. So I think that entire process was probably about an hour. I sped it up into about 10 minutes. But that's probably just due to my poor software engineering more than anything. If you'd like to take a look, then just go to the link. You can just have a look at the slides or come and see me. But basically search for window research, and we'll get it there. So with that, I'd like to say thank you very much. Cheers.